Okay, so this is term 2, week 8 physics. I won't open notes and explain, so I'm just going to explain as I go since there's not much time, but it's very easy, so I'm going to fly through it, okay? First question is reflection of a wave. It says a pulse here in a rope reaches its end, which is free to move up and down a pole. What's going to happen to the reflected wave? Basically, waves can reflect, okay? So let's say you have your wave, okay? And you send a wave like this, okay? You send it, right? You send it like this. There are two cases. The first case is on a fixed end, okay? When you have a fixed end, when it reflects back, it's gonna look like this, okay? So the rule is when it's fixed, it's inverted, okay? The speed is the same speed, and same amplitude. Okay, so this is when it's a fixed end. What does fixed end mean? معناتها here it's tied. Okay, it can't move on the end. Okay? However, if it's a free end now, if it's free to move, okay, like the example they gave on the book was a pole that had a ring, so the ring can go up and down. Okay, ونفس الشيء بتعطيها pulse. Okay, when it reflects, it's not going to be inverted. It's going to be the same thing. Okay? So that's the only difference. The only difference now here is that it's not inverted. Alright? It's not inverted. It's also same speed and same amplitude. طيب, you need to know that why does it get inverted, okay? The whole inverting thing happens is because into when you supply the force to the pole, right? It kind of like pushes the pole up. The pole, you guys know Newton's third law, for every action has an opposite and equal reaction. This was in the book, huh? So in case it comes, it gets inverted because the pole pushes the rope down as a reaction to the rope pushing the pole up. So here, into your rope, it's coming, it's pushing the pole up, right? As the reaction, what does it do? It pushes it down. So that's why for a fixed end, it will push it down and it will be inverted. But for a free end, since there's not going to be any action reaction, why? Because now it's free to move. So it's not going to push it up. When it pushes up, it's actually going to move along with it. But here it resists it and pushes it back down. Okay, when it's on a fixed end. Okay, so that's reflection. So here it's free to move up and down a pole. Which of the following will happen to the pulse upon reflection? Obviously it won't be inverted because here they said what? It's free to move. The speed increases? No. Frequency remains the same. Amplitude remains the same. Speed remains the same. Okay? The only thing that changes, actually nothing changes. It reflects back with the same thing when it's free to move. The only time it would change is when it's fixed end, and that would invert it. The wavelength slightly increase. No, it doesn't. Okay? Question 2. The diagram below shows crests of waves spreading out from a point source. What is the wavelength? Okay, so I'm gonna introduce 3 new things called wavelength over here. 1 second. Frequency, period, and wavelength. Okay, you need to know that when you have a wave, okay, heck, okay, this is one wave, right? I'll actually extend it because I need to go a bit more and show. Okay, and again up here, right? So this is like a wave and it's 2 pulses, right? You need to know 3 terms. The first term is period, second term is frequency, and the third term is wavelength, written with this symbol lambda. Okay, like this is better. Okay, period is the time it takes for one oscillation. Okay, the frequency is the number of oscillations per second. The wavelength is the distance per oscillation. Let me explain one by one. Okay, so period. Let's say here you have time in seconds, and here you have, I don't know, let's say height, right? Also I'll put amplitude. Here I have, I don't know, x in meters. Okay, the period is the time for one oscillation. So let's say this is one full oscillation, right? Let's say over here this is, I don't know, 50 milliseconds. Okay, that means the period of the graph will be 50 milliseconds. Okay, like math. How long does it take for one? Frequency is the number of oscillations per second. You can't really see it on a graph unless they give you a big graph and there's like seconds, but most of the time you're going to use this formula. Frequency is equal to 1 over t. Okay, you're going to use this formula. The second one is wavelength. It's the distance per oscillation. You can't find the wavelength from this graph of this wave. You're going to tell me, Walid, why can't you just look at the distance? Why can't you? Because here the length of the wave, we don't have it because it's labeled as time. So the only time you can find wavelength is when you're using a distance axis over here. Okay, so if you have a distance axis, then let's say this was, I don't know, let's say this was 5 meters. Okay, then here the length of the wave lambda would be 5 meters. Okay, you can also, it's also defined by something else. Wavelength is also defined by the length between each what do you call it, let's say crest, yeah, between each crest. So you could say this over here, this is longer, it should reach here only. I don't know why I went all the way there. You can also call this the wavelength from crest to crest. This is also the wavelength. Also from trough to trough. Okay, so from here to here, this is also the wavelength. So these are all things you can use to measure wavelength, in case maybe sometime they might only give you this part of the graph and ask you to calculate wavelength. So you can go from crest to crest or trough to trough or length of the wave. Okay, it's called wavelength, so you could say length of the wave. Amplitude is what the height reached by the graph. So obviously this here will be the amplitude. We have a formula. V is equal to lambda f. Okay, please memorize this. Okay, the speed of the wave is equal to the wavelength times the frequency. Okay, very easy. We're gonna come back to that. Here, this diagram shows the crests of waves spreading out from a point source. So crest to crest to crest. طيب هنا they gave us they gave us the length between two crests is 6 centimeters. They're asking us to find the wavelength. We said the wavelength is distance from one crest to another crest, but here they give us the distance from two crests. So أكيد what we do, we just do 6 divided by 2 is equal to 3. ما بدها هالقد. Okay. Question 3. Okay. A rope is made of two pieces. Oh, okay. One denser than the other. An upright pulse is emitted from the lighter piece towards the denser piece. Which of the following states best describe the behavior of the pulse at the boundary between the two mediums? Okay. Let me explain refraction. So I'm recording, yeah. So let's say you have a rope which is loose, okay, هيك عادي, it's chill, okay, and then it's connected to another dense part of the rope. I'll call it this, okay. So we're gonna call this the less dense place, and this is the more dense. Okay, so there's two cases. The first case is that you transmit a pulse from the less dense to the more dense, as I'm doing here. Well, there are two characteristics. Okay, here's how it's gonna look. It's gonna come back reflected invertedly. Okay, it's gonna go inverted, and a small part will be transmitted. Okay, I'm gonna use this as the thick one. Okay, so the first case is when you're going from less dense to more dense. There will always be a reflection. Okay, there will always be a reflection. The reflection, there's gonna be a reflection and there's a transmission. Okay, that's always. Some of it reflects back, some of it transmits. The reflection, you need to know that the reflection is inverted. Okay, and you need to know that the transmitted one, the transmitted pulse, is slower. Okay, this is what you need to know. These two. However, if you're going from more dense to less dense, think about it like this. Now for more dense, you're supplying more energy, right? Because to move a more dense rope, you're gonna need to supply more energy. So do you think that the transmitted pulse will be slower or faster? Obviously faster. Why? Because to get the more dense rope to move, you need to supply more energy. So there's gonna be more energy moving forward. Okay, so it's actually gonna look like this. It's gonna reflect, but when it reflects, it won't be inverted from more dense to less dense, and the transmitted pulse will be faster. Okay, so what do you need to know when you're going from more dense to less dense? Okay, reflected is upright, it's not inverted. Okay, and the transmitted pulse is the transmitted pulse is faster. Okay, very easy. So over here, a rope is made of two pieces. An upright pulse is going from the lighter towards the dense, so less dense to dense, more dense. Okay, which of the following describes the behavior at the boundary? Okay, so we know that it's reflected in an inverted manner. We're going from less dense to more dense, it's reflected invertedly. Is it reflected upright? No, right? The incident wave is transmitted at a lower speed. Yes, we said yes. The incident is transmitted at higher speed. No, we said no. When you're going from less dense to more dense, you don't have a lot of energy, so it's gonna be slower. A part of the incident wave is transmitted in an upright manner. Yes, the one that's transmitted, we told you guys, when it's transmitted, refraction, yeah, when it's transmitted, it's always upright, huh? You can see. Okay, question 4. Before moving on to question 4, there's just a note I wrote in my copybook saying that this reflection and refraction, it conserves the frequency. Okay, so if they ask you what causes the conservation of frequency, it's going to be the reflection and refraction over here. Okay. Match each term. Obviously, frequency is number of cycles per second. Speed is obviously distance per time. Stupid. Wavelength is the length of wave from one peak or crest or whatever. And amplitude is the height or displacement, maximum displacement. Right? Question 5. Consider 4 diagrams. Which graph is the loudest? Okay. Sound. Sound. You need to know pitch and loudness. Okay? The first thing you need to know is that frequency depends, or sorry, the pitch of a sound depends on frequency. Just call this depends. It's not necessarily directly proportional. The second thing is the loudness, okay, depends on the amplitude. Okay? Well, the third thing is sound intensity. Intensity depends on depends on this amplitude squared. Okay, let me go to one more. Pitch directly proportional to frequency. Frequency we know is how many per second. Which one's gonna have a higher pitch? This or this? Obviously this one, because there's more cycles per second. So when you have a high pitched voice, okay, there's a higher frequency. When you have a louder voice, there's a louder amplitude. Which one's louder? This or this? Obviously the one on the left, right? And then intensity is directly proportional to amplitude squared. Obviously, the higher the amplitude, the higher the sound intensity. Here I have written, the intensity of a sound is the rate at which it carries energy away from the source to a unit area at right angles to the direction of travel of the wave. Intensity, you need to know, is directly proportional to the square of wave amplitude, as I wrote here, okay? You need to know sound travels at the same speed in the same medium, okay? To show that, okay, there's an experiment. This is Yap. You can read over the book if you want. Okay, which graph here is the loudest? Obviously, the one that's loudest is the one with the higher amplitude, and the one with the higher amplitude is B. Which has the highest pitch? The one that has the most frequency, which is D. Very easy. Question 6. Okay, reflected waves. Reflected waves, I'm gonna fly through it because it's very easy, okay? You need to know waves obey the same laws of reflection as light. We had light before last year in grade 10, okay? Let's say you have a boundary like this. Draw the normal, kind of draw it like this. This will be my normal over here. يكون perpendicular. يكون لا ما بدي هيك. يكون هيدي تكون something like this. Heck. Okay, this is the normal. Let me erase this because it's a shitty arrow. We'll go like this. We'll use green. If you use sound or any wave, it comes onto a boundary. It's gonna reflect back with the same angle. Just make it perfect. Heck. Okay, so this, we're gonna call it the incident pulse, okay, incident, and this is the reflected one, right? You need to know these two angles are what? Equal, right? This is the blue one, is what we call the boundary. It's the same thing, but you need to know something new called the wave fronts. Wave fronts are these imaginary lines. You're gonna see them, okay? These imaginary lines that are spaced equally, called the wave fronts, okay? The distance between each wave front is what we call the wavelength, okay? So here, this is lambda 1. And then the reflected wave actually also has wave fronts. And these wave fronts, by the way, always are 90 degrees perpendicular to the wave, okay? So let me kind of make this drawing a bit better. حط لك هيك, okay? هيك. Okay, this is the reflected ray. If you know these are all right angles, okay, you need to know that lambda here, the wavelength here, lambda 2, you need to know when it's reflected, lambda 2 is equal, sorry, what? Lambda 1 is equal to lambda 2. Okay, this is your magic formula. Okay, when you have reflection. This is how it goes. So these wave fronts are imaginary perpendicular, what do you call it? Imaginary perpendicular lines that represent the wave. Okay, so over here, let's say you go to a reflector. What's gonna happen is gonna bounce off with the same angle. So we can continue like this. It's gonna bounce off with the same angle. Is it gonna be this? Obviously not. This obviously not. This obviously not. Yani these are very, very, very stupid answers that you could get. Okay, please don't get this question wrong in your exam. Question 7. A ripple tank is set up to hold two regions of water, deep and shallow water. An oscillator is used at one end of the ripple tank to create a water wave as shown below. So you need to know one thing. When you have different depths of water, I have it written somewhere here, refraction of the wave occurs. What do you need to know? You need to know that when you go from deep water to shallow water, how do you know this? Deep water is the speed of waves in deep water is actually faster than that in shallow. How do I remember it? In deep water, there's more space for the wave to move. Shallow water, there's less space for the wave to move. So that's why I consider it faster in deep. So if they give you a graph like they did here, okay, you can see the incident ray coming here. It moves, it continues, it refracts. Why does it refract? It refracts towards normal. This isn't important, but it comes towards the normal. It doesn't move away. No. Why doesn't it? Because it's moving from dense to less dense. Wait. Yeah, you're going, deep water. Since you're faster in deep water, this is actually less dense, right? We said we're faster in deep water because there's more space, there's less dense. In shallow water, it's denser. Okay, when you're going from less dense to dense, it deviates towards the normal. Okay, we know this from last year's optics chapter, the light, whatever. If it was the other way around, going from shallow to deep, it's gonna look like this. Okay, if they come to you in the exam, okay? It's gonna deviate away from the normal, okay? So what do you need to know? We need to know in deep water, frequency is always the same. For a wave, frequency is always the same. You need to know, look at this. V is equal to lambda times F. If frequency is the same, okay, and you know that obviously in shallow water it's slower, that's deep water. We're talking about deep water. Deep water, it's faster. So that means if you know frequency is the same, that means if you want to increase the velocity or the speed of it, that means you need to increase the wavelength. So that's a way. If you know that the speed is faster, then that means immediately you should know that the wavelength is faster because V equals lambda F. Okay, so memorize. In deeper water, it's faster. It has the same frequency and it has a higher wavelength. Okay. Question 8. This diagram shows a ripple tank as seen from above, an oscillator generating straight waves toward a gap. How will the water waves behave after they pass the gap? There's a concept with waves and light called diffraction. Okay, the thing is about diffraction is when you have a small hole, okay, and let me show you. One. I'm gonna use water as an example, okay? So let's say you have, I don't know, water wave. These are the wave fronts. I'll draw them for you in green, okay? Right, these are the wave fronts. Imagine they're the same, but just for practicality, I'm gonna go a bit fast. Okay, so you have over here a gap. Okay, you set up a gap. See how we have two gaps? So imagine you have like a lot of waves coming here, and they see a gap. Basically, what they do in the gap is they concentrate. Okay, after that, the waves are actually gonna look like this over here. See how they have curved ends? Okay. And the wavelength still remains the same. Okay, this is how it kind of looks. But the wavelength should be the same. So let me move this a bit over here. Okay. So what do you need to know? You need to know that when you have gaps like this, light will diffract, as in it will focus. Okay, not light, waves. Sorry, waves will diffract. They will focus on somewhere. Okay, these gaps, they're wide. You need to know the wider the gaps are, the straighter the waves are. Okay? So I'm going to draw for you another example now with very small gaps. Oh, I can't go down. Oh, I can't. It's the end of the page. Okay. I'm going to draw for you now one with small gaps. These are the wave fronts. Okay. Coming through here. Over here, very small gaps. Okay. And come in here. How's it going to look? It's going to look like this. See how they're curved? So the smaller the gap, the more curved. Okay? You need to know that light behaves both as a wave and as a particle. Okay? So light actually obeys diffraction. But you guys know, wait, light, how's light? When did we say light is a wave? So you need to understand that light can behave both as a wave and as a particle. Okay? You just need to know that in case it comes in a multiple. So when you have any hole over here or gap, when you have a wave, it's gonna diffract. Okay? You need to know also one more thing, that there are some things that affect the amount of diffraction. Obviously, the first one being the width of the gap. How wide is the gap? How wide is the gap? How long is the gap? Okay. The second thing is the wavelength of the water wave. If you have a higher wavelength, then the diffraction will kind of be larger. So, like, they used something in the book called the Young-Slit experiment. I'll open the book now and show you. It's for light. I'm pretty sure they should have mentioned it at least once. No, they didn't. Wow. Here. Apply single slit. Yeah. Okay. Yeah, so this is the Young-Slit experiment. Basically, this guy, he put two holes, okay, and then he put laser sources and he sent them through, okay. Basically, when any wave passes through a hole, we told you it diffracts like this, okay. What do you need to know? You need to know that you're gonna see beams that overlap. What do I mean? These beams, when they overlap, they cause interference. Yeah, for what I was saying is beams overlap superposition interference. When you have two beams that intersect, okay, it's gonna cause interference. Basically, what happens when you have two waves, one coming like this, one coming like this, and another one also coming like this, and they interfere with each other, they create one big wave, okay, and that causes an image. However, when you have one big wave coming like this and one wave coming like this, obviously they're gonna cancel out. Okay, so this is the reason why we get bright and dark images. You need to know that in the middle, you see how they all have intersections? This is called the central bright fringe. Above it will be the first dark fringe, above and below, and then after that will be bright fringe. It's always alternating. You see how it goes? Okay, you see how this line, intersections, intersection, intersection. But the dark fringe, there's nothing. Look, you see? There's nothing. So where there's no intersection, it's dark. Very, very, very calm, very easy. Okay, this is how it looks. Okay, you can see a pattern of dark and bright lines. That is what the Young-Slit is. Okay, let me go back. You need to know if the wavelength of the light is higher, then the gaps between the bright and dark images will be bigger. Okay, you need to know that. Same thing here. If the wavelength of the water wave is bigger, then the diffraction will be bigger, so the gaps will be larger between the waves. Okay, density machas, this doesn't matter. Okay, question 10. Okay, the wavelength of the wave is 25 centimeters and its frequency is 1200. What's the speed? Speed is equal to, V is equal to lambda times F. Lambda times F. Okay, lambda has to be in meters. So this is 25. I don't work with it. I only work with 0.25 times the frequency 1200. You get 300. Question 11. Two pulses of equal amplitude in the opposite sense are moving towards each other and meet at point A. Obviously, they're going to cancel out. What is this called? Destructive interference. Interference can either be destructive, as in they destroy each other, or constructive, as in they add up. Okay, they construct a bigger and larger wave. Question 12, it's constructive if they're both upright, or both inverted. Okay, if they're one upright, one inverted, it's going to cancel. Question 12. Select the graph that shows a periodic wave. When I say something is periodic, that means it repeats itself. Like the periodics we do weekly, right? We have periodics every week, okay? That means they repeat themselves. This isn't periodic because how is it periodic? It's not moving. This also, it's not like it's good. It's just staying upright. Someone might choose this. Why is he wrong? Because look, is it the same period throughout the whole wave? Obviously not. It's decreasing, Okay, so the only one with the same periodic repeating is this one, the one above. Question 13. Which of the following intervals represent the period of this wave? Period is the time taken for one oscillation. So obviously you can say from O until D, right? Can you say BD from here to here? No, obviously not. Can you say, let's say, AE? Let's see, what's AE? From from trough to another trough. Obviously, that's completely fine. I told you can go from trough to trough or crest to crest. CE? No, you can't. You can't go from crest to trough. No. Okay? You cannot do that. I told you from crest to crest or trough to trough. OD, we said yes, it's correct. And OC, no. Why? Because it still has to go back down. Okay, so it's actually, one way to think about it, it's the time taken to go from one point to the adjacent point on another wave. Okay, so if you want to start at 0, you have to end at 0. If you want to start at a crest, you have to end also at another crest. If you want to start at a trough, you have to end at another trough. Very easy. Question 14. The number of waves that pass through a fixed point per second is called frequency, right? What graph can be plotted if we hold position constant? Okay, they want to talk about this. Is that it? Is that the one? Okay. Obviously, if you hold the position constant, can you do displacement? Like مثلا here, over here, go to the left. Okay, over here when I was working with this, I told you can have either displacement time or displacement. Why do I work with it? Sometimes when you hold displacement constant, you want to look at the time. How long does it take for each oscillation? So that's when you take displacement time. Okay. If they held time constant, what do you do? Or if they're not considering time, you can't hold time constant. You're going to look at displacement graph. Okay, what does the crest to crest interval represent? In displacement time, crest to crest, you're looking at what? Period. But if it was displacement, what would it be? Wavelength, right? I told you displacement time, the distance from crest to crest would be period. But if they change it to displacement, it's going to be wavelength. Okay, question 16. Okay, fill in the blanks to complete the table below. Okay, so they're giving us the speed, the frequency, then we want the wavelength. Using the equation V is equal to lambda times F. Okay, to find the wavelength, lambda is equal to V divided by F. So 3 divided by 2, 1.5. Frequency is equal to V divided by lambda. So 3.9 divided by 1 is 3.9. And then speed, V is equal to lambda F. So 5 times 3, which is 15. Okay. Question 17. Which of the following are true about a high pitch note? I told you pitch depends on the frequency, right? It has a high frequency. Does it have high wavelength? No. Low energy? Who said? No. It has a long period? No. It actually doesn't have it. It has a short period, right? It has a short wavelength. You need to know one thing, okay? That frequency is inversely proportional to wavelength. The higher the wavelength, the longer the wavelength, that means there's a less frequency. So anytime you see high frequency, that means wavelength is the opposite. Please know this, okay? Frequency and wavelength, they don't go together. They don't go in the same sentence. So if you have a high frequency, there should be a low wavelength. If there's a high wavelength, it should be a low frequency. Okay, we know high pitch, that means a key high frequency. We don't know anything else other than it has a short wavelength. Does it have low energy? No. Does it have a long period? No. Okay? Question 18. The loudness of a sound depends on what? Obviously, amplitude. We said amplitude. Question 19. The diagram below shows a displacement of soil during propagation of a wave along the surface of Earth after an earthquake. What kind of wave is shown in the diagram below? We can see what? It's propagation along the surface of Earth. So you're going through a medium. So obviously it's going to be a mechanical wave, right? We know that it's going to be longitudinal. Why? Because you can see compression and refraction, right? When you see compression and refraction, that means it's longitudinal, because you can't have compression and refraction in a transverse wave. Remember from last 2 weeks ago. So it's going to be a longitudinal mechanical wave. Underline the point at which compression is observed and circle refraction. Obviously, compression is observed over here at point 1 and point 3, and refraction is observed over here at point 2 and point 4. Why not point 5? Because point 5, you can see it's kind of like in the middle. It's like in between small and big. So that's just a normal wave. Okay. Question 20. Speed of sound in water is greater than speed of sound in air. Many people get this wrong. In our mock, actually, many people got this wrong. Do you need to know this? Okay, because it came in our mini mock. Maybe it gets it for you guys. Speed of sound. Okay, speed of sound in air and water. Okay, in air it's 340 meters per second. Okay, In water, it's 1500 meter per second. Speed of light in air is light, okay, is 3 times 10 to the power of 8 meter per second. And in water, it's 1.6 times 10 to the power of 8 meter per second. Let me Google this way. My bad, is not 1.6 times 10 to the power of 8. It's 2.25 times 10 to the power of 5 meter per second. Okay, if you want to memorize this, you can go ahead, but he asked us about these two. Okay, so speed of sound in water is actually the opposite. It's faster. It's faster in water. Speed of light in water is less than speed of light in air. See, so it's the opposite. You see, speed of sound in water is less than speed of light in water. Obviously, light is always going to be faster than sound, whatever you do. Okay, and speed of infrared radiation in air, speed of visible light in air. This is important. Okay, the electromagnetic spectrum. Electromagnetic spectrum, you go read it by yourself. But because we did it last year, it's over here. If any my SDP works, over here, the electromagnetic spectrum. You need to know one thing. Okay, oh, come back. Okay, you go from radio waves to normal like radio waves to microwaves. So you go radio waves to microwaves to infrared to ultraviolet to gamma rays or X-rays. Okay, what do you need to know? You need to know that as you go from right to left, wavelength lambda decreases. As you go from right to left, lambda decreases, velocity increases. Okay, صح? Frequency. What? Sorry, velocity doesn't change. My fault. قصدي frequency is the one that increases. I told you, when wavelength decreases, frequency always increases. Okay, so radio waves actually have such high wavelengths, okay, but very low frequency. And as you go to the left, frequency increases, okay, and wavelengths decrease. Okay, you can read over this if you want. What do you need to know? You need to know that the velocity of all of these are the same. All types of light will be 3 times 10 to the power of 8 meters per second in air. No matter, infrared, gamma, X-ray, I don't care what, it's all going to be 3 times 10 to the power of 8. Okay, so speed, as long as they're in the same medium, any wave in the same medium has the same speed. Question 21. A property of sound determined by the amplitude, obviously loudness. Property that depends on frequency, pitch. A rate at which it carries at a right angle, you say intensity. Okay, I mentioned this earlier. Question 22. Two pulses of amplitude 5 centimeters and 3 centimeters meet at point O. If they interfere constructively, Akid, what do? You add them. If destructively, you subtract. It's so easy. Okay, so they're interfering. It's so easy. Question 23. In order to locate their prey, a bat sends out sound waves. When the sound waves hit an object, they bounce off the object and return to the bat ears. A bat listens to the echo produced and figures out where the insect is and how big it is. A bat can emit sound from 12 kilohertz to 160 kilohertz, given that the speed of sound in air is 340 meters per second. The sound with the longest wavelength is what? We know the frequency. We know the frequencies, and we know the speed of sound. Can we find wavelength? We know V is equal to lambda times F. How do you find lambda? It's equal to V over F. But what? They give us the smallest frequency and they give us the highest frequency. They want what? The longest wavelength. If I want the longest wavelength, which one am I going to choose? The lowest frequency or highest frequency? I always tell you, longest wavelength, wavelength and frequency don't go together. So if you want longest wavelength, that means you're going to choose the shortest frequency. Okay, so the velocity is 340 over the frequency, which is in kilo, kilo, so multiply by 10 to the power of 3. Okay, so 340 over 12 times 10 to the power of 3, you get 0.0283. They want in millimeters, so let's multiply by 1000. You get 28 to the nearest integer. Okay, the bat hears the echo 0.05 seconds after it screeches. The insect that the sound wave bounces off to one decimal place is something meters away. So they give us the time it took and the speed that it's traveling at. Can't you find the distance? Of course, we know speed is equal to distance divided by time. So you're going to know 340 is equal to the distance divided by 0.05. So how do you find distance? You cross multiply. You're going to get 17. So we're going to tell you the answer is 8.5. Now look. it's 0.05 seconds. So what does an echo do? An echo travels forward, then comes back, right? So all of this is 17 meters. And I'm not asking how far the path is. I'm asking how far is the how far is the insect? So is a killa 17 meters, and you know it travels twice. It goes towards it and comes back the same distance back to the bat. So what do you do with this? You have to divide it by 2. Okay, so you get 8.5. Super easy. Okay, question 24. Always with echoes, you 99% of the time you have to divide by 2. Okay, consider a light passing through a small slit projected on a screen. The light pattern is shown below. What is the phenomenon? We said it's diffraction, obviously. Okay, dark, bright, dark, bright, dark, bright. It's diffraction. What phenomenon explains the fact that 7 additional light fringes are seen to the left and right of the central slit? So notice here how they say light fringes. When we say light fringes, there's bright, there's an image. So what is it going to be? Destructive interference or constructive? Obviously constructive. Okay, super easy. Question 25. An electromagnetic wave has a wavelength of 120 millimeters in vacuum. Which part of the electromagnetic spectrum does it belong to? Okay, nanometers in vacuum. Now, I don't want to tell you memorize them, because I'm not sure if you should memorize them. From what I know, I don't think you should memorize. But let's take a look at the wavelengths. Okay, the typical wavelengths, when you get to nanometers, you're at ultraviolet. So kilometers, the longest wavelengths, I told you, the longest wavelengths come from radio waves. Meters would be microwaves, like the microwave you have in your kitchen. Millimeters would be infrared. Okay, micrometers would also be infrared. Okay, and then when you hit nanometers, it's ultraviolet. Okay, and then picometers, it's X-rays, gamma rays. Okay, so I think you can memorize it like this. It's not that hard. Okay, the frequency of this electromagnetic wave is what? Type. How do you find frequency? We have the wavelength, lambda. We have the speed, even though it's not given, we're saying in vacuum. And we know we're talking about light. So obviously V is equal to 3 times 10 to the power of 8 meters per second. عندك lambda بدك frequency. What do we use? We use V is equal to lambda times F. Okay? You need to assume in vacuum that the speed of light is 3 times 10 to the power of 8 meters per second. So how do you find frequency? It's 3 times 10 to the power of 8 over 120 times 10 to the power of negative 9. You can tell me, well, شو negative 9? Nano is times 10 to the power of negative 9. PM for picometer is times 10 to the power of negative 12. Okay, that's how it works. Milli is obviously times 10 to the power of negative 3. If you want micro, its symbol is like this, is times 10 to the power of negative 6. Okay, so you get 2.5 times to the power of 15. We're done. Thank you so much for watching, and good luck in your exam.